You've seen already in this unit how there's a close connection between parametric equations and vector equations. And really, you could really think about them as just two different ways of thinking about or writing down the same idea. And the idea is how you can define paths that would be difficult to express as Cartesian equations because there isn't a clear relationship, there isn't a clear direct relationship between x coordinates and y coordinates. So you would need to define the position as a function of something else, like time. Designers who design fonts use design tools that use parametric and vector equations as part of them so that it makes it easy to define these kinds of curves without having to understand all of the mathematics yourself. And so today's problem is going to be thinking a little bit about the mathematics that goes into those design tools. But before you dive into the problem, it's worthwhile thinking about why are fonts not defined as little tiny pictures of letters. You know, when you type, like, why is it the case that there are equations involved at all? So the most common format for pictures on a computer are what's called a raster format. And a raster format is just a grid of pixels that are each a uniform color. The problem with this kind of format is they're not scalable. You zoom in far enough and you get a pixelated image, just like the one that you see here. But if you've ever done something like make a poster, you know that in Microsoft Word, there's no limit to how large you can make your letter form. You can select it and you can set the font size to be 100, 200, 500, 800. And you never see any pixelation at all. And the reason why you never see any pixelation is because letter forms are defined by equations. And you know from Desmos that you can zoom in infinitely on an equation and it will remain smooth. It will never pixelate because you're continually generating new coordinates the further you zoom in based on the equation that's the rule. So that's a good reason why it would make sense to use equations for letter forms. It's because it makes them scalable. Another reason is it takes actually quite a lot of memory to define the color of every single pixel. But if you think about the amount of information that's contained in an equation is a very short piece of text. There's only a couple of pieces of important information. So if you needed to stream video, if you're streaming video that consists of different pixel colors, that's going to require quite a lot of bandwidth to stream the video. But if instead you're streaming information about equations, the person on the other end can reproduce the same pictures using far less information. So that's called information compression. And so equations are also used as a way of compressing information so that you don't have to send the picture itself. Instead, you can send mathematical information that can be used to regenerate the picture. So here's a picture of one of the design tools. Whoops, there we go. Here's a picture of one of the design tools. You can't see the person's cursor, but they're dragging around some of these control points, and the overall shape of this fancy G is changing in response to the control points. So I said it's all mathematical equations. These are actually piecewise defined parametric functions that are creating this font shape. But the designers themselves don't work with those equations. Instead, they just work with these control points, and then the equations responds to the location of the control points. This is one example of a parametrically defined curve that's based on 3 control points. You got the 2 endpoints, and then you have a point that defines kind of the middle. And you can see that you could, if you had a bunch of these that were kind of put together ends to end, you could define a letter shape. So this is the first problem, and you can do the 2 problems in either order. And you can read more details about kind of how this is defined in the problem statement itself. But before we do that, I want to show you the other one. The other one you can see is also based on 3 control points. 2 are the endpoints. But this one, you can see it just kind of pulls the curve in that direction, but the curve never directly touches it. So how does this actually work? The way this works is a very clever use of vector-based motion. You already know how to make a point move along a linear path. So let's call time equals 0 this control point, and time equals 1 that control point. So I want to make a point move at a constant speed from this point to that point. And that's going to be one equation. And then I also want a point to move at constant speed from this point to this point, from time 0 to 1. So here's what that would look like. So even though it seems like quite a long time passed there, it was just time going from 0 to time going to 1. So I have two different equations. So let's visualize what would happen if we drew a line between those two moving points. It would look something like this. All right. So here I've paused it. This seems like it's maybe time like 1/4, because time 0 is here and time 1 is there, and it seems like maybe I've gone 1/4 of the way along that path. So let's now define a third moving point. We've got two moving points. The third moving point at time 0 is going to be at the location of this point, and at time 1 is going to be at the location of that point. And it's going to move at a constant rate between these 2 points, which are also moving. So what would that look like? Here you go. So time 0 to time 1, you've got that point that's defined as motion along a linear path, but the linear path is also defined in terms of the motion of its endpoints. Okay, so last piece of the puzzle here. If I'm going to add a line, or if I'm going to add a curve that shows me the path that's traced out by that middle point, it looks like this. And so as you can see, that's the magic behind how you calculate where is this path so that it connects the two endpoints, but this third point over here still pulls the curve in a particular direction, but the curve never actually meets that third control point, that middle control point. So that's the second problem. It might seem like this one's a lot more complicated than the first one, but I think they're actually about comparable. They just have different complexities involved.